Today we're going to talk about this wiffle ball rotating in a vertical circle. Now we're going to start and lead up to that way. And we'll start with the string just holding the wiffle ball still. So if the string's job is to simply hold up the wiffle ball, then the sum of the forces must equal 0. We've been talking about that. And if my force diagram simply has the tension up and the weight down, then we know that ultimately the tension has to equal the weight. Well, the next step in this process is if the wiffle ball is going to accelerate upwards. If the wiffle ball is going to accelerate upwards, then the string kind of has two jobs. It must first just keep the wiffle ball here, and then it must accelerate the wiffle ball. So in the case of this acceleration, the string has two jobs. So in the second case here, the string's job is to hold up the wiffle ball and accelerate it upwards. So we're going to make ourselves a progression that ultimately leads us to this vertical circle that we want to talk about. So if the string's job is to hold the wiffle ball and accelerate it upwards, the force diagram still looks the same. So if I take the string here and use it to accelerate the ball upwards, the only two forces still acting on the string are the tension and the weight. But because it's accelerating upwards, we know that the tension must be bigger than the weight. Well, how much bigger? Well, as it turns out, it's equal to an amount times m times a bigger. So how does that look, right? So sum of the forces, there's an acceleration, has to equal m times a. And sum of my forces is t minus w equals m times a. So then therefore, t equals w plus m times a. And we've kind of been through this process already. Let me make the a look nicer. We've been through this process already. If the a value is 0, then this term goes away, and lo and behold, I'm actually back to my first situation over there. So you can see that the tension has one job here, then it adds a second job. It balances this weight. Then we got to have a little bit more to cause an acceleration. Now the next step in the process was taking this wiffle ball and twirling it into a horizontal circle. Now it's tough to make this thing go exactly horizontal, but we can give it a whirl. We can do the best we can. Now what's important here is this. If I freeze framed this right here, there's actually two forces acting on this thing. Weight pulls it downwards, and the tension in the string is pulling it back towards the center. Well, as soon as we see a circular motion, we're worried about what is providing a centripetal force. So in this particular case, while the weight still acts on this, again, the weight is straight downwards. The only things that can provide centripetal force are things that act radially or in the plane of the radius of the circle. And in this case, the only thing that's doing that is the tension in the string. So if we were to talk about what happens in this particular situation, and I'm going to do that on a sideboard here so that my progression doesn't kind of get harmed here. So as soon as we see circle, then the sum of the forces is equal to mv squared over r. And in this case, and actually, as in all cases, anytime we do this, these are only radial forces, we call them. And those are forces that act in the plane of the radius of the circle. In this particular case, again, the only thing that is acting in the plane of the radius of the circle is the tension. So we have tension equals mv squared over r. So we have this progression. Now, what makes our next situation different, I'm going to leave this on here for now. What makes our next situation different, if we make this circle vertical, and to make our lives easier, we're really only going to talk about the very top of this circle and the bottom of this circle. And if I freeze frame this ball at the bottom of the circle, now again, remember this thing is going around in a vertical circle, and I freeze frame it down here at the bottom of the circle. Now, if I freeze frame this thing at the bottom of the circle, my force diagram still looks exactly like this. In other words, if I have this thing here, if it's going around in a circle, I still, at the very bottom, have tension pulling up and the weight pulling down. So my force diagram doesn't change. What changes, however, is the acceleration. So when the string's only job up here is to accelerate the ball upwards, I want to make a special note with respect to this acceleration. It's accelerating by changing its speed. In our new situation, the string has two jobs again. String's job, I'm gonna specify this, at the bottom of a vertical circle is to hold the ball up and keep it in the circle. Now over here, the string's only job is to counteract weight, is to keep the thing still. Over here, its job is to hold the wiffle ball up and change its speed. In reality here, what the string is doing at the bottom of this circle is it's holding the ball up and changing its direction. So over here, when we talk about the wiffle ball accelerating upwards, the tension is holding the string still and changing its speed upwards. Here, when I twirl this thing in the circle like this, it's, if I freeze frame it again down here, the string's job is to hold it up and keep it going in the circle. It's not accelerating it up and down. It's not just holding it. It is keeping the ball in the circle. So it's got to hold the ball up at the bottom and change its direction to keep it in the circle. Well, anytime we see circle, sum of the forces equals mv squared over r. Now down here at the bottom, again, I still have the same force diagram here. Still tension up and weight down. So it's still T minus W equals mv squared over r. Which means that the tension will equal W plus mv squared over r. Again, two jobs. If the string is not moving, right? The string's not moving in this circle, right? At the bottom, if it's not moving, then the tension's going to equal the weight. If it's moving in this circle, then the tension's got two jobs. Hold the ball up and keep the thing in the circle. Now look at these two statements here. They're super similar. Let me underline them in blue here. These two things are super similar. The only thing that separates the two is that this thing over here has an A in it, and this thing over here has a v squared over r. Those two things basically are equivalent to each other. And what I'm saying by that is, let me put a little arrow, right? Because I don't want you to think that this acceleration is equal to that. However, this is an acceleration. What type of acceleration? Again, very specifically, we've talked about this. This is the centripetal acceleration of the object. What is this? What is this caused by? This is caused by a change in direction. What's this thing caused by right here? This acceleration here is caused by a change in speed. Now notice, if I were going to substitute in for this acceleration, it would be delta V over delta T. If I'm changing the number, this is a linear acceleration. This is a delta V over delta T. Notice over here, this is just simply a velocity. In other words, this object is accelerating even if its speed around the circle is staying the same. Why is it accelerating? Well, because it's constantly changing its direction. It's undergoing a centripetal acceleration. So we can see that the math is very similar, but we have slightly different jobs for the string. Change the speed, change the direction, and therefore a different type of acceleration over here and a different type of acceleration over here. Now our next progression along this line is to talk about what happens up here at the top of the circle. Now what happens up here at the top of the circle is that tension doesn't even have one full job, right? So tension here had a full job. Over here, tension had two jobs. Hold the thing up and accelerate it vertically upward by changing its speed. Over here, tension had two jobs. What were the two jobs? Well, hold the thing up and keep the object in the circle. Over here, when we're talking about at the top of the vertical circle, the string shares one job at the top of the vertical circle. Right, so think about that. Like if your parents gave you one job to do, okay, that's all right. Now they give you two jobs. That's a little bit more difficult. They give you two jobs over here. They're just two different jobs. Here, they give you a job, but you share it with something else. So you have actually less than one job over here. The string's got less than one job over here. It shares its job at the top of the circle with the weight. Now, what is its job? Its only job at the top of the circle is to keep the object in the circle. So what's its job, right? The job is to keep the ball in the circle. Right? Because what was the one job that's common to all three of these things? The one job that's common to just holding this up, or holding it up and changing its speed linearly, or holding it up and keeping it in the circle, the one thing that's in common here is that the string held the ball up in all of these situations. Well, if we're talking about this vertical circle and I freeze frame this thing up here at the top, the string is not holding this ball up anymore. It's pulling it down towards the center of the circle. Well, what else is pulling the ball down towards the center of the circle? Well, the weight is pulling the ball down towards the center of the circle. So for the first time in our little discussion here, the force diagram changes. So here's my wiffle ball, and again, that's now at the top of the circle. Now I've got tension here, and I've got mg, or the weight of the object. Let me put W. That'll make it easier to keep us in line with what's going on right here. There's my W. They're both going down in the same direction. If I was going to draw the picture kind of for this little setup, I'd have my circle, and the wiffle ball would be here, and I'd have tension here and weight here. Again, just like this picture over here. So now when I do the sum of the forces equals mv squared over r, again, why do I do that? Because the word circle is popping up. Anytime we have circular motion, that's what we're going to do. Now, these two things are helping each other. So I'm not going to subtract them. It's t plus w equals mv squared over r. Now look at the math here. We've got math over here where the limit over here, let me get rid of this stuff. There's a limiting factor over here because the string can only do so much. In other words, if I put this thing super fast, this V value gets bigger and bigger and bigger and bigger and bigger. Well, in order for the ball to stay in the circle, what's on the left has to equal what's over here on the right. So this tension has to be equal to the weight plus mv squared over r. So here we have basically an upper limit of V based on the strength of the string. In other words, that string can only sustain so much. It's easy for the string to do this. And then as we get going faster and faster and faster, it's harder for the string to do its job to keep this thing in the circle. And eventually, if we got this thing moving fast enough, the string would reach its breaking strength. And then therefore, the wiffle ball would fly off in a straight line because the string isn't capable of doing these jobs anymore. We have the opposite happening over here. W can't change, just like W can't change over here. W can't change over here. So we have this minimum value that can occur over here on the left. So the left part of this, so the left side has a minimum of W. Well, then the tension in the string at this minimum would be W. So think about this, right? While this side talks about the limitations of going fast, at the top we have limitations of going slow. Because if we go too slow, the ball falls out of its circle. Well, why does the ball fall out of its circle? Because look at, if this thing weren't moving, then weight's job is to pull this thing down. Right now, weight is helping to keep the object in the circle. And weight can do this job by itself if the tension in the circle is zero. In other words, if it's tough to see probably on the screen, but the wiffle ball's going slow, so the tension in the string actually becomes zero. It becomes limp like this up here at the top of the string, or at the top of the circle. So when this T becomes zero, the left side reaches its minimum. And that minimum is equal to the weight of the ball. Well, now if we don't want the ball to fall out of the circle, then mv squared over r has to match the weight. So we have this minimum where W equals m times v min squared over r. Anything lower than this speed in the equal sign doesn't work anymore. And therefore the ball falls out of the circle. Well, what is that minimum speed? Well, let me, I think I got a little space over here. Well, if W equals mv min squared over r, and that's showing up good, W is m times g equals m v min over r, gotta square that. Well, the m's go away, and g times r square rooted equals v min. Now, we don't want you running around memorizing that. We want you to have an understanding of what's going on. And we're going to spend today talking about this situation of vertical strings in a wiffle ball. And then tomorrow we'll work on it with amusement park rides. And then the next day we'll work on it in a different situation. So you'll get a bunch of different hits with respect to the specifics of this, but they're all based on this setup of the multiple jobs of the tension in the string.